Consider a puzzle that even committed atheist cosmologists call genuinely unsolved. The early universe, the state observed in relic light from 375,000 years after the Big Bang, was thermodynamically extraordinary. It was not chaotic. It was not generic. It was not what statistical physics would predict from random initial conditions left to the ordinary laws of physics. In the precise technical sense, the early universe was highly non-generic. And nobody in mainstream cosmology has a settled explanation for why. One man has spent the last 15 years proposing one. Roger Penrose, 2020 Nobel Prize winner in physics, British mathematical physicist and author of the book Cycles of Time. His proposal is one of the most radical ideas in modern cosmology: Conformal Cyclic Cosmology. The Big Bang was not the beginning of everything. What we call the start of the universe was the conformal continuation of a previous aeon, a complete cosmic history that ended before ours began. By the end of this documentary exploration, you will understand the mathematical structure behind Penrose's claim, the disputed evidence drawn from the cosmic microwave background, the concept of conformal rescaling, the troubled idea of a Hawking point, and what this theory genuinely requires of physics. You will see where the science ends and where the deeper questions remain. If you find value in explorations like this, in understanding the puzzles that keep physicists awake at night, consider subscribing to the channel. It helps these deep dives reach more curious minds. Now, let us begin. To understand why Roger Penrose proposes that our universe existed before the Big Bang, you must first understand the puzzle he is trying to solve. It is not the puzzle most lay people hear about in popular cosmology. It is something subtler, stranger, and far more difficult to dismiss. The mainstream account of cosmic history begins with the hot Big Bang. The universe was once dense and hot. Then it expanded and cooled. About 375,000 years after that beginning, the plasma of free electrons and protons recombined into neutral atoms, and light, for the first time, could travel without being immediately scattered. That light has been traveling ever since. It is the cosmic microwave background. Its temperature today sits at about 2.725 Kelvin, which is roughly minus 270.4 degrees Celsius, or minus 454.8 degrees Fahrenheit. It bathes the entire sky. Every direction we look, that ancient light is there. The standard model that fits this universe is called lambda CDM. The name encodes its ingredients: a cosmological constant called lambda plus cold dark matter. The model has 6 free parameters. When the European Space Agency's Planck Space Observatory delivered its final cosmological analysis, those parameters were tightly constrained. The Hubble constant came in at 67.4 kilometers per second per megaparsec, give or take half a unit. The matter density parameter, omega m, was 0.315, with a precision of 7 thousandths. The spectral index of primordial fluctuations, NS, was 0.965. The amplitude parameter, sigma 8, was 0.811. 6 numbers. The entire visible cosmos, statistically described by 6 numbers. This is, by any measure, a profound result. Lambda CDM fits the data with a precision earlier generations of cosmologists would have considered impossible. But fitting the present is not the same as explaining the past. And here is where Roger Penrose departs from the mainstream consensus. The early universe, in his analysis, is not merely well described by lambda CDM. It is, in a deeper sense, an embarrassment for any account that treats it as a brute initial condition. The point can be stated cleanly. The second law of thermodynamics says entropy increases with time. Look at any isolated system in a laboratory. Drop a hot stone into a cool bath, and the system moves toward equilibrium as entropy rises. Time has a direction because thermodynamics has a direction. This is not just chemistry. It is one of the deepest statements physics has ever produced. Now run the logic in reverse. If entropy rises with time, then earlier states must have had lower entropy than later states. The further back in time you go, the lower the entropy must have been. Push that logic all the way to the Big Bang, and you are forced to a conclusion. The universe began in a state of extraordinarily low entropy. Picture a room filled with gas molecules. Most arrangements of those molecules look uniform. Statistically, almost every possible configuration looks like a uniform gas. But a small subset of configurations, vanishingly small in the mathematical sense, has all the molecules clustered in one corner. That low entropy configuration is special. The high entropy configurations are generic. The low entropy configuration is rare. The early universe, when you look at it correctly, was that rare configuration. Not in matter, not in radiation, in gravity. This is the part that takes a moment to absorb. The early universe looked smooth, almost perfectly uniform. The cosmic microwave background varies in temperature across the entire sky by only 1 part in 100,000. To a casual reader, this looks like high entropy because the system looks like an equilibrated gas. But Penrose's point is the opposite. When gravity is the dominant force, and at cosmic scales gravity is the dominant force, smooth means low entropy. Clumpy means high entropy. A universe full of black holes has astronomically more gravitational entropy than a universe full of evenly spread gas. The early universe was smooth. Therefore, in gravitational terms, the early universe was extraordinarily ordered. This ordering is what Penrose calls the Weyl Curvature Hypothesis. The Weyl tensor is a mathematical object in general relativity that encodes the free gravitational degrees of freedom. The Weyl tensor captures, roughly, how much gravity is doing work that is not directly tied to local matter. At the Big Bang, in Penrose's formulation, the Weyl curvature was zero, or at least so close to zero that the gravitational field was effectively unexcited. This matters because it means the universe began in a thermodynamic state so special that it accounts for almost the entire arrow of time. The reason coffee cools rather than heats up. The reason memory points backward rather than forward. The reason cause precedes effect. All of it, traced back, depends on the universe starting in a low-entropy state, a state that, statistically, no generic cosmology should expect. The mainstream response to this puzzle, when it acknowledges the puzzle at all, is cosmic inflation. The theory of inflation, originally proposed by Alan Guth and later developed by Andre Linde and others, proposes that in the first fraction of a second, the universe underwent an exponential expansion, smoothing out any initial irregularities and stretching quantum fluctuations into the seeds of cosmic structure. Inflation is the standard early universe complement to lambda CDM. It has had successes. Predictions of nearly scale invariant fluctuations, captured by the spectral index NS of 0.965, match observation. But Roger Penrose is not satisfied. His objection, set out as early as 1989 in his paper Difficulties with Inflationary Cosmology, is that inflation does not actually solve the entropy problem. To work, inflation requires its own special initial conditions, a particular kind of vacuum state, a particular initial Weyl curvature, a particular configuration of the inflaton field. The fine-tuning has not been removed, it has been relocated. We will return to this assumption later. This is the puzzle that drives conformal cyclic cosmology. Not what came before the Big Bang, that is the popular framing, and it is not wrong, but it is shallow. The deeper question is this: why was the early universe so non-generic? Why was its gravitational entropy so low? What kind of explanation could possibly make sense of a beginning so improbable that it accounts for the very direction of time? Penrose's answer is geometry. To see how the answer works, consider what happens to our universe in the very far future. The cosmological constant lambda is positive. This is known from observations of distant supernovae made in the late 1990s that revealed cosmic expansion is accelerating. The universe is not just expanding, it is expanding faster. And if the cosmological constant remains positive, that acceleration will continue indefinitely. Run the clock forward. Stars exhaust their fuel and die. Galaxies recede beyond each other's horizons. Black holes grow, then evaporate, releasing their mass energy. In the slow trickle of Hawking radiation, the universe becomes colder, emptier, less structured. Eventually, far enough into the future, every star has burned out, every black hole has evaporated, every particle of matter has decayed or radiated away. What remains is a vast, dilute, exponentially expanded sea of low-energy photons in a de Sitter-like geometry. The heat death of the universe. In this remote future, something strange happens to the very concept of size. When everything is photons and gravitational waves, when there are no clocks, no rulers, no rest masses to define a scale, the absolute size of the universe stops being physically meaningful. What remains meaningful is conformal structure, angles, light cones, the causal relationships between events. Stretching the universe by any factor leaves these unchanged. In a universe with no rest masses, there is no way to distinguish a vast, cold expanse from a small, hot one. The geometry is conformally equivalent. Think about what this means with a simple comparison. Picture a photographer with a roll of film. He develops the negatives at one scale. He prints them at another scale. The information is preserved across the scaling. The angles in the image are unchanged. The relationships between objects are unchanged. Only the absolute size has shifted. In conformal geometry, what matters is the relationship, not the size. Roger Penrose's outrageous suggestion, and that is the phrase his colleague Paul Todd uses with affection rather than dismissal, is that the future conformal boundary of one universe can be smoothly attached to the Big Bang of the next. The exponentially expanded, infinitely dilute, conformally stretched final state of one cosmic history becomes the hot, dense, conformally compressed beginning of another. He calls each of these full cosmic histories an aeon. Our universe is one aeon. There was an aeon before ours. There will be an aeon after. The chain extends in both directions, indefinitely. There is no first beginning. There is no final end. Only an endless succession of eons, each joined to the next by what Penrose calls a conformal crossover. This is Conformal Cyclic Cosmology. The book version of the idea was published in 2010 under the title Cycles of Time. The current paperback edition runs to 304 pages. What does it mean that a respected mathematical physicist of Penrose's stature is now proposing that the Big Bang was not the beginning at all, that it was a boundary? It means the question of cosmic origins is not closed. It means the standard story, explosion, expansion, cooling, structure, does not exhaust what serious physicists are willing to consider. And it means we are about to walk through a very specific, very mathematical, and very contested proposal for what came before the beginning. This is the part that stays with me. Not the audacity of the proposal, the reason for it. Penrose did not invent conformal cyclic cosmology because he wanted speculation. He invented it because the mainstream account of the early universe, taken on its own terms, is genuinely strange. The early state was too ordered, too special, too thermodynamically unusual to be brushed aside as just the way things are. We will return to that strangeness in due course. For now, hold on to the structure. An aeon is a complete cosmic history. A crossover is the boundary where one aeon ends and the next begins. Conformal rescaling is the mathematical operation that allows the boundary to be smooth. The Weyl curvature was zero or near zero at our Big Bang. And Penrose argues this is because the previous aeon's future boundary delivered it that way. The arrow of time in this picture is inherited. It is a striking idea. We will spend the next portion of this exploration looking carefully at the mathematics, the empirical claims, and the missions that have tested those claims. But before we leave the foundations, one further point must be made. Conformal cyclic cosmology is, by its own author's design, not the mainstream view. Lambda CDM with inflation remains the working framework of professional cosmology. CCC has supporters, collaborators, and a handful of empirical claims attached to it, but it is a minority position. When you hear the popular phrase, "Penrose says the universe existed before the Big Bang," you are hearing a real claim made by a real Nobel laureate. You are not hearing a settled scientific fact. That distinction matters. We will keep it in view throughout. The cosmic microwave background, the relic radiation that carries whatever signature of an earlier aeon would, in CCC's logic, be detectable, was first measured by NASA's Cosmic Background Explorer, the COBE spacecraft. COBE launched in 1989. Its findings, announced to the public in April of 1992, established two facts that became foundational for all subsequent cosmology. First, the cosmic microwave background has an almost perfect black-body spectrum, with a precision better than 1 part in 1,000. Second, it contains anisotropies, variations in temperature from one direction to another, at the level of about 1 part in 100,000. Without those anisotropies, no galaxies could have formed. Without them, we would not exist to observe anything. NASA's Wilkinson Microwave Anisotropy Probe, called WMAP, launched on the 30th of June 2001. WMAP operated until 2010. The probe positioned itself near the second Lagrange point of the Sun-Earth system, scanning the full sky every 6 months from a stable gravitational location about 1 million miles, or roughly 1.5 million kilometers, from Earth. Its instruments observed in 5 frequency bands, from 23 to 94 gigahertz, with an angular resolution of about 13 arc-minutes. The full-sky CMB maps from WMAP became, for nearly a decade, the most detailed picture humanity had of the early universe. Then came the European Space Agency's Planck Observatory. Planck launched on the 14th of May 2009. The observatory also took up residence near the second Lagrange point, observing the entire sky in 9 frequency bands, from 30 to 857 gigahertz. Planck's primary mirror was 1.5 meters across, or roughly 4.9 feet. Its angular resolution ranged from about 5 to 33 arc-minutes, depending on the channel. Planck delivered the highest precision full-sky maps of CMB temperature and polarization in human history. These 3 missions, COBE, WMAP, Planck, form a ladder of increasing precision. Every empirical claim made by Conformal Cyclic Cosmology rises or falls on whether the patterns it predicts can be detected in maps from this ladder. Every counterclaim, every critique, every rebuttal eventually returns to the same question. Is the signal really there, or does it disappear when the data are analyzed more carefully? Pause for a moment on what the cosmic microwave background actually represents. Picture a long-distance hiker walking through fog. He cannot see far. The fog is dense. Light scatters in every direction. Then, as the temperature drops, the moisture condenses and falls to the ground. The fog clears. From that moment onward, the hiker can see for miles. Now reverse the picture. From any point in our universe today, looking outward and backward in time, the universe is transparent until we look back to about 375,000 years after the Big Bang. At that age, the cosmic plasma cleared. Photons could finally travel without being immediately scattered. The cosmic microwave background is the wall of fog at the moment it cleared, frozen in our view, on the last scattering surface. Anything happening before that surface is hidden behind the fog. Conformal cyclic cosmology asks, in effect, whether faint patterns from before that fog could have left signatures we can still detect on its surface today. Keep this question in mind. We will need it. Now consider the mathematical operation at the heart of conformal cyclic cosmology. In general relativity, the geometry of space-time is encoded in a metric tensor, written G sub AB. The metric tells you how to measure distances, durations, and angles between any two nearby events. Einstein's field equations relate the curvature of this metric to the matter and energy it contains. In speakable form, the equation reads G sub AB plus lambda G sub AB equals 8 pi G over c to the fourth times T sub AB. The left side describes geometry. The right side describes the matter and energy distribution. The cosmological constant, lambda, sits between them, a constant that, in the modern view, drives the accelerated expansion of the universe. Every aeon in CCC obeys these equations. The theory is not a rejection of general relativity. It is a radical proposal about boundary conditions. To describe the geometry of an expanding universe in practice, cosmologists use a particular form of the metric known as the Friedmann-Lemaitre-Robertson-Walker metric, after the four physicists who developed it in the early decades of the 20th century: Alexander Friedmann, Georges Lemaitre, Howard Robertson, and Arthur Jeffrey Walker. In speakable form, the FLRW line element reads ds squared equals c squared dt squared minus a of t squared d sigma sub k squared. The scale factor, a of t, describes how the universe grows or shrinks with cosmic time. The term d sigma sub k squared captures the spatial geometry, with the parameter k specifying whether space is flat, positively curved, or negatively curved. Within this framework, the rate of expansion is governed by what is called the Friedmann equation. A dot over A squared equals 8 pi g rho over 3 minus k c squared over a squared plus lambda c squared over 3. The variable rho is the total energy density. The first term on the right is the gravitational pull of all matter and radiation. The middle term is the curvature of space. The third term is the contribution of the cosmological constant. The mainstream background universe, and the simplified aeons in conformal cyclic cosmology are usually described in this FLRW form. The mathematics is compact. It is also, on its own, silent about why the actual early universe occupied such a special trajectory within the vast space of possibilities the equations permit. The FLRW framework can describe many different histories. Only a tiny subset of those histories produces the universe we observe. The framework does not, by itself, explain why our particular history was selected. The crucial mathematical step in CCC is the conformal rescaling. In speakable form, G tilde sub AB equals omega squared G sub AB. The new metric, G tilde, is the old metric multiplied by the square of a function called the conformal factor, omega. Conformal rescaling preserves angles. It preserves the structure of light cones. It preserves causal relationships. What it does not preserve is absolute distance. Stretch the universe by a factor of 100, compress it by a factor of 100. The geometry has changed, but the conformal structure has not. Penrose's argument is that in the remote future, when no rest masses remain, the absolute scale of spacetime ceases to have physical meaning. Only the conformal structure carries information. And if only the conformal structure matters, then the future of one aeon, its conformally rescaled remote future, can be identified with the conformally rescaled Big Bang of the next. The technical bridge is captured in what Penrose calls the reciprocal hypothesis. In speakable form, omega hat times omega check equals -1. Omega hat is the conformal factor relevant to the previous aeon as seen from the crossover. Omega check is the conformal factor relevant to the next aeon. Their product is fixed at -1. From this, an explicit relationship emerges between the metric of one aeon and the metric of the next. G check sub AB equals omega hat to the -4 times G hat sub AB. In plain language, CCC is not a vague philosophical claim. It is a specific mathematical prescription. Given the geometry of one aeon at the crossover, the geometry of the next aeon is determined. But there is a problem here, planted as a seed for what we will examine later. The conformal factor must be chosen. The mathematics gives a relationship, but it does not by itself fix omega uniquely. We will return to this point in due course. For now, accept the structure. Aeons, crossover, conformal rescaling, reciprocal hypothesis. These are the mathematical pillars. There is one more pillar to introduce before this section closes. Penrose's framework requires that in the remote future, all rest masses effectively vanish or become irrelevant. This is the part that gives technical cosmologists the most pause. Photons are massless. Gravitons, if they exist, are massless. but electrons have mass. Protons, neutrons, even neutrinos all have rest mass. For CCC to work geometrically, these massive particles must either decay to massless ones, or their rest masses must somehow fade to zero over cosmological time. Consider what this assumption asks of physics. Picture a draftsman working on a blueprint that must remain accurate at any zoom level. The blueprint specifies relative angles and proportions perfectly, but it depends on every measurement in the design being scaleless. The moment a single fixed dimension enters, a beam of definite length, a rivet of definite size, the blueprint loses its scale invariance. CCC asks the universe to be that kind of blueprint at the crossover. Every fixed scale must somehow vanish before the geometry can be conformally re-identified with the next aeon's beginning. Whether this can actually happen for electrons, protons, and other massive particles in our world is, by Penrose's collaborator Paul Todd's open admission, unresolved. Todd's words on this section of the theory are blunt. It is, in his phrase, all questions and no answers. We will return to that admission later. Beyond CCC itself, Conformal Cyclic Cosmology is not the only cyclic cosmology proposal in serious physics. The ekpyrotic and cyclic cosmology family, associated with the theoretical physicists Paul Steinhardt and Neil Turok, proposes a different mechanism altogether, one in which the Big Bang corresponds to the collision of two higher dimensional surfaces called branes, and the cycle includes both expansion and contraction. Loop quantum cosmology, derived from a different theoretical foundation, attempts to replace the classical singularity with a quantum bounce. These are not versions of CCC. They are siblings. Each attempts, in its own way, to push the question of cosmic origins past the Big Bang itself. CCC stands apart in its method. CCC does not invoke colliding branes. CCC does not invoke quantum bounces. It invokes geometry. Specifically, the observation that conformal structure can be preserved across what would otherwise be a singular boundary. This is its strength. It is also, as we will see, the source of many of its weaknesses. The historical context here matters. Stephen Hawking's 1974 derivation of black hole evaporation provided one of the indispensable late-time engines that conformal cyclic cosmology relies upon. Penrose's 1989 paper, Difficulties with Inflationary Cosmology, sharpened his long-standing complaint that inflation does not solve the deepest entropy puzzle. By the time COBE launched in 1989 and announced its anisotropy detection in April of 1992, the foundations were in place. The cosmic microwave background was no longer a theoretical prediction. The CMB had become a precision instrument for testing cosmological proposals. WMAP's launch in June of 2001 and Planck's launch in May of 2009 then turned that instrument into the most discriminating probe of early universe physics ever built. Through this same period, Penrose was developing conformal cyclic cosmology in private correspondence and gradually in public lectures. The 2010 publication of Cycles of Time made the proposal accessible to a broader audience. Almost simultaneously, the first observational claim, the Penrose preprint on low-variance circles, appeared in November of 2010. The book and the preprint together launched the modern phase of CCC. From that point onward, the story divides into two interwoven streams: a theoretical development at the level of mathematics and physics, and an observational program at the level of CMB statistics. We have just walked through both. Now we must examine what survived contact with rigorous criticism. The data, the missions, the mathematics, the motivation, all of it points to the same simple structure. Roger Penrose claims our universe is one aeon in an unbounded sequence. He claims the low entropy of our beginning is inherited from the previous aeon's end. He claims the Weyl Curvature Hypothesis follows naturally from this, rather than being imposed by hand. He claims certain features of the cosmic microwave background, features we are about to examine in detail, are signatures of events in the previous aeon. These are large claims. They deserve careful examination. This brings us to the next phase of the inquiry. The mathematics of conformal cyclic cosmology is one thing. The empirical claims attached to it are another. From 2010 onwards, Roger Penrose and a series of collaborators have argued that specific patterns visible in the cosmic microwave background, patterns visible in the data from WMAP and Planck, are signatures of events that happened before our universe began. We must now examine those claims in order, with care. The first major empirical claim emerged in November of 2010. Roger Penrose and Vahe Gulzadyan, an Armenian mathematical physicist born in 1955, published a preprint titled, in essence, that the 7-year WMAP sky maps contained anomalous features they identified as evidence of pre-Big Bang activity. The claim was specific. Around certain points in the sky, the temperature variance of the cosmic microwave background appeared abnormally low when measured in concentric annular rings. Their search swept annular widths of half a degree. The radii ran from 2.5 degrees to 16 degrees in steps of half a degree. They reported a statistical significance, in their words, up to 6 sigma, an extraordinary claim if true. They had a physical interpretation. In the previous aeon, before our Big Bang, supermassive black holes encountered one another. Each encounter released a vast burst of gravitational radiation. The wavefront, in CCC's geometry, propagates conformally through the crossover and imprints itself as a circular pattern in our cosmic microwave background. The center of each pattern marks the location of the encounter event in the previous aeon's universe. The concentric rings mark successive bursts. To check whether their result was an artifact of the WMAP instrument, Gulzadyan and Penrose examined data from Boomerang, an independent CMB observation experiment. They reported that similar features appeared there as well, taken by them as evidence that the patterns were real and not instrumental. The claim made global headlines. The popular phrasing was almost irresistible. Evidence of a universe before the Big Bang. Articles followed in major newspapers. Documentary segments were filmed. Penrose, already famous as a Nobel laureate-to-be, became one of the most discussed cosmologists in the world. We will return to whether the claim survived scrutiny. 2 years later, the program continued under different leadership. Krzysztof Meissner, a Polish theoretical physicist born in 1961, and Paweł Nurowski of the Center for Theoretical Physics of the Polish Academy of Sciences published their own analysis with collaborator Ruszczycki. They argued that the WMAP sky contained ring-type structures distinguishable from artificially generated statistical maps at the 99.7% confidence level. The framing was slightly different from the original Gurzadian-Penrose claim, but the underlying logic was the same. Real patterns existed in the CMB, patterns that did not match what one would expect from a purely Gaussian random field. Later, the same collaboration extended their analysis to the higher precision Planck data. Working with Daniel Ahn, a mathematician at SUNY Maritime College, they reported that one angular scale in particular looked unusually significant in Planck maps. A value of gamma equal to 0.14 radians, which corresponds to about 8 degrees on the sky. They argued this preferred scale supported the existence of CCC-relevant structures in the cosmic microwave background. We will return to whether these claims also survived scrutiny. Then came the most publicized observational claim of all: Hawking points. The name itself is a reference to Stephen Hawking, whose 1974 derivation of black hole evaporation provided the late-time engine that CCC's observational program depends on. Hawking radiation is the slow leak of energy from a black hole's horizon, predicted by quantum field theory in curved spacetime. In speakable form, the Hawking temperature of a black hole is given by T sub h equals h bar c cubed over 8 pi gmk sub b. The variable m is the mass of the black hole. The other terms are fundamental constants. The essential feature of this equation is that the temperature is inversely proportional to the mass. Smaller black holes are hotter. Larger black holes are colder and evaporate more slowly. Run the equation over cosmological time, the smallest black holes evaporate first. The largest evaporate last, over timescales so vast they exceed any conventional cosmic chronology by many orders of magnitude. In a far future de Sitter universe, the very last objects to vanish are the supermassive black holes that lay at the centers of galaxies, including giants like Sagittarius A star at the center of our own Milky Way. Their final evaporation would take, in Penrose and Meissner's later estimates, on the order of 10 to the power of 112 years, a number with no useful comparison in human experience. In CCC's scheme, that final evaporation is not a meaningless ending. It is a signal. The very last burst of energy from a supermassive black hole in the previous aeon's distant future propagates conformally through the crossover and arrives in our aeon as a hot circular spot in the cosmic microwave background. Before we move further, one more equation deserves attention here. The entropy of a black hole is given by the Bekenstein-Hawking formula, derived by Jacob Bekenstein and Stephen Hawking in the 1970s. In speakable form, S sub BH equals K sub B times A over 4 L sub P squared. The variable A is the area of the black hole's event horizon. L sub P is the Planck length, and K sub B is the Boltzmann constant. The remarkable feature of this equation is that black hole entropy scales with the area of the horizon, not with the volume enclosed. A black hole the mass of the Sun has more entropy than the entire visible universe, evenly distributed in radiation, would have without it. This is why Penrose's gravitational entropy argument depends so heavily on black holes. Picture an accountant trying to balance the universe's entropy ledger over cosmic time. In the early universe, with no black holes and smooth gravitational fields, the gravitational entropy line on the ledger is essentially empty. By the late universe, when supermassive black holes dominate the centers of galaxies, that line has grown to staggering proportions. The total entropy has increased by a factor that, by Penrose's estimates, is so vast that the early universe's ordering accounts for almost the entire arrow of time. Without that initial low gravitational entropy, the second law of thermodynamics would have nowhere to point. What does it mean that one equation, Bekenstein-Hawking entropy, links the most extreme objects in the universe to the most fundamental statement about time itself? It means the question Penrose is asking is not peripheral. It sits at the meeting point of gravity, thermodynamics, and the structure of cosmic history. That is what Daniel Ahn, Christoph Meissner, Pavel Nurowski, and Roger Penrose proposed in 2018, in a paper later published in the journal Monthly Notices of the Royal Astronomical Society in 2020. They reported anomalous circular spots of raised temperature in the CMB, with radii between 0.03 and 0.04 radians, about 1 7/10 radians, about 1 7/10 degrees to 2 3/10 degrees, or diameters of roughly 3 to 4 degrees on the sky. They argued the size cutoff looked as though it came from point-like sources at the conformally stretched Big Bang. They called these features Hawking points. Picture what this would mean if true. Each Hawking point in our cosmic microwave background corresponds to an entire supermassive black hole that finished evaporating in the previous eon's far future. Each marks the death of a galactic center from a universe that ended before ours began. Each is, in a sense, a memorial, preserved through the geometric scale erasure of crossover and printed onto the relic radiation of our own beginning. Whether they are actually that is precisely the question we will examine in due course. For now, take note of the intellectual move. The CCC observational program has progressed through 3 claims. First, low-variance concentric circles attributed to gravitational wave bursts from black hole encounters. Second, ring-type structures at preferred scales, attributed to other large-scale events in the previous eon. Third, hotspots, called Hawking points, attributed to the final evaporation of supermassive black holes. Each claim more specific than the last, each requiring increasingly sophisticated statistical analysis to defend. What does it mean that a single theoretical framework has generated 3 different empirical signatures in 15 years, each of them contested? We will return to that question. The most recent development on the theoretical side of conformal cyclic cosmology came in 2025. Roger Penrose and Christoph Meissner published a paper that attempts to address one of the long-standing weaknesses of CCC, the question of what exactly happens at the crossover from one eon to the next. The original CCC proposal, dating back to the 2010 book Cycles of Time, was geometrically elegant but physically incomplete. The proposal described how space-time should fit together at the boundary, but it did not say with full rigor what fields and what particles do during the transition. Penrose and Meissner's 2025 paper proposes that just before the crossover and just after, the universe is dominated by gravitational waves. They argue that this gravitational wave epoch makes the conformal crossover smooth, except at discrete points. And those discrete points correspond to Hawking points, the same hotspots claimed in the 2018 observational paper. They go further. They propose a mass-energy conservation law that holds across the crossover surface. The temperature rise observed in a Hawking point in our cosmic microwave background, in their interpretation, reflects the total mass of the entire galactic cluster that ended at that location in the previous eon. The numbers they cite are vertiginous. Cluster masses on the order of 10 to the 15th solar masses. Evaporation lifetimes around 10 to the 112th years. The gravitational wave epoch beginning at a scale factor of about 6 times 10 to the 16th, occurring approximately 103 billion years after the present cosmic epoch. These are not measured numbers. They are theory internal extrapolations, predictions that follow from CCC's mathematical framework if every assumption holds. We will return to the question of whether those assumptions hold. The 2025 paper also makes one further claim that deserves careful attention. It states, plainly, that the standard early inflationary phase of cosmology is necessarily absent in CCC, and that the effects which inflation is usually invoked to explain, the smoothness, the flatness, the spectrum of fluctuations, can instead be attributed to the previous eon's final exponential expansion. This is one of the boldest claims in modern cosmology. It is also, by mainstream consensus, not currently supported by observation. The logic here is worth pausing on. Cosmic inflation, the standard early universe story, predicts that quantum fluctuations during the inflationary epoch were stretched into the seeds of cosmic structure. Penrose's alternative is that those same seeds came from gravitational and other dynamics during the previous eon's de Sitter-like end, which was conformally identified with our beginning. The mathematics, in the abstract, is workable. The empirical case for it is not yet established. This is where we must keep the foreshadowing in mind. Earlier, we noted that Penrose's objection to inflation is that it does not solve the entropy problem. It only relocates it. we will return to whether his alternative solves the problem any better. There is a second mathematical structure in this 2025 paper to record. The conservation law for mass energy across crossover is what allows Penrose and Meissner to interpret the temperature elevation of a Hawking point as reflecting a total previous eon cluster mass. If the law holds, then in principle, observation of multiple Hawking points across our sky could be used to reconstruct a partial census of supermassive structures in the previous eon. That is a striking possibility. It is also predicated on a chain of assumptions, several of which remain open. Notice what this requires. The conformal factor must be uniquely fixable. The mass fade-out must be physically real. The crossover must be smooth, except at discrete points. The discrete points must correspond, one-to-one, to the final evaporation events of supermassive structures. Each of these assumptions is, in the existing literature, contested. Yet, all of them together are required for the 2025 picture to deliver what it claims. We are building towards something. Stay with me. The technical center of CCC, then, can be summarized in a few key elements. First, the geometric proposal. Future conformal infinity of one eon is identified with the Big Bang of the next via a conformal rescaling. Second, the entropy proposal. The Weyl Curvature Hypothesis at our beginning is inherited from the previous eon's smooth, unclumped late state. Third, the empirical proposal. Signatures of previous eon events, black hole encounters, large-scale structures, final evaporations, are encoded in our cosmic microwave background. Fourth, the recent proposal. A gravitational wave epoch dominates the very late universe, smoothing crossover, except at the Hawking points themselves. The whole picture is mathematically demanding, geometrically beautiful, and observationally fragile. Consider, in concrete terms, what it would take to confirm any of these claims. The cosmic microwave background you have ever heard of is a single sky. There is no second observable universe to compare it to. Every statistical test must therefore use simulations as a baseline. Generate many fake skies under the standard lambda CDM assumptions. Compare the real sky to them. If the real sky has features the simulations almost never produce, you have evidence of something beyond the standard model. The catch is that the test is only as good as the simulations. If your simulation baseline is wrong, if it fails to capture some legitimate feature of standard cosmology, then patterns that appear anomalous might simply be normal CMB structure your simulation did not properly include. Picture a marine biologist examining samples from what she is told is a freshwater lake. She analyzes the chemistry. She compares her samples to a baseline of typical freshwater values. She finds anomalies, concentrations of certain salts that do not appear in her baseline. She reports the anomalies, perhaps even speculates that they reflect contamination from outside the lake. Then someone reveals that her freshwater baseline was wrong. The lake is actually a brackish estuary, and the salt levels she called anomalous are exactly what brackish water normally produces. The signal was real, its interpretation was not. This is the fragility we will return to in the next part. For now, note the structural problem. CCC's empirical claims rely on detecting patterns that are subtle, statistical, and potentially confounded by simulation choices. Every paper in the program, from Gurzadyan and Penrose in 2010, through Meisner and Nurovsky in 2012 and 2013, through Ann, Meisner, Nurovsky and Penrose in 2018 and 2020, has been challenged on exactly these grounds. Before we examine those challenges, one more piece of the story needs to be recorded. The technical literature on CCC contains, in addition to the bold claims, a remarkable number of admissions about what remains unsettled. Paul Todd's writings on the formalism state that the field content near crossover and the rules for conformal matching remain open. Oliver Markwell and Chris Stevens, in a 2023 paper, write directly that the choice of conformal factor is, in their phrase, a major open problem, and call it a fundamental hurdle for the framework. They also state that some conformal factor choices proposed in the literature can be ruled out. These are not external critics. These are technical commentators working within or alongside the CCC tradition. Their assessments matter precisely because they are sympathetic. When even sympathetic commentators describe central elements of a theory as unresolved, the theory is not in a settled state. It is still under construction. Keep these admissions in mind. We will return to them. What does it mean that 15 years after Cycles of Time was published, the central mathematical question of how to choose the conformal factor remains, by sympathetic admission, a major open problem? It means CCC, even taken on its own terms, is not yet a complete theory. It is a proposal, an audacious, mathematically rich and partially developed proposal for how cosmic origins might be reconceived. That is not a flaw in the theory. It is a description of where the theory currently stands. CCC is not a finished structure. It is a building under construction, with sections that work, sections that are sketched, and sections that are explicitly open. The question now is this. When CCC is presented to the public as evidence that the universe existed before the Big Bang, the science does not yet support that confidence. When the headlines say, "Penrose proves the universe is cyclic," the proof is not there. This brings us to the third part of our examination. For the past hour and a half, we have presented Conformal Cyclic Cosmology as its proponents presented. We have walked through its mathematical structure. We have surveyed its observational claims. We have noted the missions, the people, the equations, the timelines. We have been fair to the theory in the way every audacious idea deserves to be heard fairly, by stating it in its strongest form before. Testing it. Now we test it. Earlier, we planted 3 foreshadowing seeds. The first, the entropy problem inflation was supposed to solve. The second, the empirical claims that depend on subtle statistical interpretation of one sky. The third, even sympathetic technical commentators admit that central elements of CCC are unresolved. We promised to return to each. We do so now. Begin with the empirical claims. The 2010 paper by Vahe Gurzadyan and Roger Penrose reported low-variance concentric circles in the WMAP data, with significance up to 6 sigma. The claim was extraordinary. The response was, in the timing of professional cosmology, almost immediate. In December 2010, less than a month after the original preprint, 3 cosmologists at the University of British Columbia, Adam Moss, Douglas Scott, and James Zibin, published their own analysis. They reproduced the Gaussian-Penrose search exactly. They generated standard Gaussian lambda CDM simulations of the cosmic microwave background. They ran the same statistical test on those simulations. They found the same circles. Their summary sentence remains the core objection. Properly simulated Gaussian CMB data contain just the sorts of variations the original paper claimed as anomalous. The patterns were not signatures of a previous aeon. They were what standard cosmology already predicted. Gaussian and Penrose had rediscovered, with sophisticated statistics, the simple fact that the cosmic microwave background has structure. Around the same time, Ingunn Veihus and Hans Christian Eriksson at the University of Oslo reached the same conclusion by a different route. Their 2010 reanalysis of WMAP showed the observed low-variance circles were fully consistent with lambda CDM simulations. Their 2011 follow-up, responding to a Gaussian-Penrose rebuttal, argued that the CCC team's simulations had used an inappropriate power spectrum, the wrong baseline for comparison. The methodological critique was sharp. The CCC team had compared the real sky against a simulated sky that was not, in fact, what standard cosmology predicts. Amir Hajian's 2010 reanalysis came to the same place by a third route. He reported that the famous concentric low-variance circles were not anomalous, and that the highlighted groups were consistent at the 3 sigma level with a Gaussian CMB sky predicted by inflationary cosmology. 3 independent teams, 3 independent routes, the same conclusion. The original CCC empirical claim did not survive contact with proper analysis. Think about what this means with a careful comparison. Picture a forensic investigator who claims to have found unusual patterns of footprints in the sand around a crime scene. He calls them anomalous. He attributes them to a specific suspect. Then 3 independent forensics teams arrive. They examine the same patterns. They take their own simulated sand surfaces, walk on them in ordinary ways, and find the same kinds of patterns appearing naturally. The anomaly was not anomalous. It was what unmarked sand does when ordinary feet walk on it. That is what happened with the 2010 circles claim. The patterns were real. Their significance was not. The CCC observational program continued, but each subsequent claim has met a similar fate. The ring-type structures reported by Meissner, Nurowski and Ruszczycki in 2012 attracted scrutiny, and follow-up analyses found that significance estimates depended sensitively on how the simulations were performed. The Hawking points claim, reported by Ann, Meissner, Nurowski and Penrose in 2018 and 2020, has likewise been re-examined. Lopez and collaborators developed a new detection method for ring-like structures and reported in their paper that no significant Hawking point-like structures were observed in Planck maps, even though their method successfully recovered 95% of synthetic anomalies in calibration tests. The instrument was working. The detector was sensitive. There was simply nothing significant to detect. In 2024, Bodnier and collaborators conducted what may be the most comprehensive analysis to date, utilizing machine learning techniques, including their Hawking net detection system. They performed a high-resolution search for low-variance circles. They ran a machine learning search for Hawking points. They were careful to control for unusually bright or dark spots can artificially inflate the statistics of earlier methods. Their conclusion was measured. No statistically significant evidence was found for either circles or Hawking points after accounting for these artifacts. Their phrasing matters. They did not say CCC is disproved. They were careful. They said, the absence of significant features does not by itself disprove the theory. But they said clearly that the current cosmic microwave background data do not positively support the CCC observational program. Picture a geologist examining what he is told is a recent sediment core. The sample comes back with layered complexity that should take 1 million years to form. He tests the core 3 different ways. Same result. At some point, he stops questioning his instruments. He starts questioning the timeline he was given. The CCC observational claims have now been examined by multiple independent teams with multiple independent methods. The results have been consistent. The original claims have not survived. At some point, the question is no longer whether the methods are good enough. The question is whether the claims were ever well supported. This is the empirical state of CCC's observational program. Bold claims repeatedly published, repeatedly reanalyzed, repeatedly found to be consistent with standard lambda CDM expectations. The signatures of a previous aeon, if they exist at all, have not been detected at any level of statistical confidence that would normally count as evidence in cosmology. What does it mean that the empirical case for conformal cyclic cosmology, after 15 years of effort, remains weak by the standards of the field? It means the popular phrase, evidence that the universe existed before the Big Bang, overstates what the data actually show. Now turn to the theoretical critiques. These are, in some ways, deeper than the empirical ones because they concern not whether CCC's predictions can be confirmed, but whether CCC is even a complete theory in its current form. The conformal factor problem is the most serious. Recall the structure. The metric of one aeon is related to the metric of the next through omega, the conformal factor. The reciprocal hypothesis fixes omega hat times omega check at -1. But this relationship does not, by itself, fix omega uniquely. There are infinitely many functions satisfying the constraint. CCC, in its current form, does not specify which one is the correct one. This is not a small technical loose end. It is structural. Without a unique omega, the aeon-to-aeon map is not uniquely determined, which means CCC does not, in its current form, predict a single specific next aeon. CCC predicts a family of possible next aeons, parameterized by the choice of omega. To fix the choice, additional principles must be added, principles that are, themselves, not uniquely determined by the underlying mathematics. Think about what this means with a concrete comparison. Picture an architect handed a partial blueprint for a building. The blueprint specifies that the next floor must be related to the current floor by a particular scaling rule. but it does not say which scaling rule. The architect has the relationship, but not the parameter. He cannot build until someone tells him from outside the blueprint what value to use. CCC, in its current state, gives the relationship between eons, but does not give the parameter that selects which next eon will actually result. Without that parameter, the construction does not proceed. Oliver Markwell and Chris Stevens, in a 2023 review, state this plainly. The choice of conformal factor is, in their phrase, a major open problem. They call it a fundamental hurdle. They also state that certain conformal factor choices proposed in the literature can be ruled out. The theory does not yet have a unique answer to one of its own central questions. Then there is the question of mass fade-out. CCC, as we have seen, requires that all rest masses become irrelevant or vanish in the remote future. Whether this can be made physically consistent with established physics is, in Paul Todd's blunt assessment, unresolved. His own words are striking. The QFT section of CCC is all questions and no answers. Quantum field theory, the framework that describes how fields and particles behave, has not been successfully integrated into CCC's crossover physics. That is not a peripheral admission. It is, in effect, the working interpreter of CCC's mathematics, telling the reader, this part is not yet a theory. It is a hope. A further line of theoretical critique comes from the quantum information community. Eckstein, Horodecki, and others have argued that CCC's assumption of information loss in black holes, the idea that the information swallowed by a black hole is destroyed when the black hole evaporates, clashes with the modern quantum information understanding of entropy. In a unitary quantum framework, information is conserved. Black hole evaporation, in the standard quantum interpretation, must preserve the information of what fell in. CCC's geometric picture, taken naively, requires loss. To reconcile the two, CCC must be modified into a unitary version, which is, again, not a peripheral adjustment. This is the cumulative pattern. Conformal factor, unresolved. Mass fade-out, unresolved. Quantum information consistency, unresolved. Empirical signatures, contested at best, undetected at worst. Inflation replacement, not supported by current data. Take the patterns together. CCC, taken as a complete physical theory, has more open questions than answers. Its strongest defenders acknowledge this. Its sympathetic technical commentators acknowledge this. The popular impression of a theory with strong evidence, the impression cultivated by headlines about evidence of a universe before the Big Bang, is, on examination, not what the technical literature actually shows. Now we come to the deeper question. Even if CCC were complete, even if its mathematics were settled, even if its empirical signatures were confirmed, what would it actually establish? The popular framing is that a theory like CCC, if true, would mean no creator is needed. The universe would extend infinitely in both directions. There would be no first beginning to require an explanation. Cosmic origins would be self-contained. This is a philosophical extrapolation, not a result delivered by the mathematics, and it deserves careful examination. Notice the structure of CCC. CCC does not propose that reality is uncaused. CCC proposes a specific lawful framework, a positive cosmological constant, a particular conformal structure, a reciprocal hypothesis fixing the relationship between eons, a mass-energy conservation law across crossover, a Weyl Curvature Hypothesis at every Big Bang. CCC does not eliminate law. CCC requires law. CCC requires a very specific, very intricate, very mathematical, lawful framework that holds across an infinite chain of eons. The question that follows is not difficult to formulate. Why does any of this exist? Why is there a conformal structure rather than no conformal structure? Why is there a positive cosmological constant rather than no cosmological constant? Why does the reciprocal hypothesis hold? Why is the Weyl curvature suppressed at every eon's beginning? Some philosophers have suggested that an infinite chain of eons removes the need for a first cause. The argument runs as follows. If there is no first beginning, then nothing began. And if nothing began, no cause is required. But this reasoning misunderstands what causal arguments in classical metaphysics actually claim. The cosmological argument does not require a first beginning in time. The cosmological argument requires an explanation for the lawful, intelligible, structured framework within which any cosmic history, including a cyclic one, operates. Imagine a clockmaker examining a clock. He notices that it is not just keeping time today. The clock has been keeping time for as long as anyone can remember. There is no record of when it was made. The argument that the clock had a maker does not depend on knowing when it began. The argument depends on the existence of the clockwork itself, on the precise gears, the calibrated springs, the lawful interactions that make timekeeping possible. Even if the clock had been ticking for an eternity, the gears themselves would still call for an explanation. CCC, if true, does not erase the clockwork, it extends it. The reciprocal hypothesis still holds. The conformal structure still operates. The Weyl curvature still vanishes at the right places. The mass-energy conservation law still functions across crossover. None of these are self-explanatory. None of these arose from nothing. They are, in the precise sense, constitutive features of the lawful framework that CCC presupposes. What does it mean that the most ambitious proposal for getting before the Big Bang still requires the same underlying intelligibility, the same structured, mathematical, non-arbitrary lawfulness that motivates the cosmological argument in the first place? It means CCC does not end the conversation about cosmic origins. It does not even shift the conversation. It simply moves the conversation to a different boundary. Now turn to the entropy problem. This was the original motivation for CCC. The early universe was non-generic. Its low gravitational entropy was extraordinary. Penrose's proposal was to inherit the low entropy from the previous aeon, where the de Sitter-like late state was naturally smooth. But notice what this requires. for the inheritance to deliver our universe's specific low-entropy beginning, the previous eon's late state must itself be smooth in the right way. And for the previous eon's late state to be smooth, that eon's earlier history must have led to a smooth late state, which requires that eon's beginning to be appropriately configured. The fine-tuning has not been removed, it has been multiplied. Sean Carroll, a theoretical physicist and science writer who is not a theist and does not advocate CCC, has stated the problem with refreshing clarity. He has written that the early universe was highly non-generic, and added, in his own words, "We don't know why. That's an important puzzle." Carroll is not a friend of CCC. Carroll represents the mainstream cosmology community, which favours inflation. And yet he acknowledges the puzzle openly. What does it mean that the deepest scientific minds, on every side of the cosmology debates, agree that the early universe's specialness is a real problem requiring an explanation? It means the explanation is not optional. Either you give an account of the specialness, or you treat it as a brute fact. CCC tries to give an account. Inflation tries to give an account. Neither, by their own technical proponents, has fully succeeded. The puzzle remains. Here is where the case for design becomes pointed. Picture a combination lock with 26 dials. Each dial runs from 0 to 1,000,000,000,000. The lock opens only when all 26 are set to specific values, not approximately, exactly. The probability of hitting the right combination at random is a number so small it has no useful comparison in human experience. But here is what makes our universe's situation stranger than a combination lock. The dials were not set by anyone turning them. They appear to have come preset from the beginning. The fine-tuning of physical constants for the existence of structure, chemistry, and life is acknowledged across the cosmology literature. The Planck cosmological parameters H0, omega m, ns, sigma 8 represent only a small subset of the configuration that had to be right. The cosmological constant itself is fine-tuned to a precision far stricter than any of these. The early Weyl curvature is fine-tuned. The strengths of the fundamental forces are fine-tuned. Each parameter could, in principle, have been almost anything. Each one, in fact, was extraordinarily specific. CCC, even if it succeeds in inheriting some of this from a previous eon, does not explain why any eon has these specific values. CCC explains, at best, why our eon got the values it has, by inheriting them from a chain. But the chain itself has those values throughout. The explanation has not solved the problem of fine-tuning. It has multiplied the problem across an infinite sequence. Some physicists respond to fine-tuning by invoking a multiverse, an infinite collection of universes with random constants, of which we happen to inhabit one suitable for our existence. This is, by the standards of falsifiability, philosophy rather than science. No other universe has been observed, measured, or detected. The multiverse hypothesis is invoked precisely to avoid the conclusion that fine-tuning suggests intention. It is, in a critical sense, naturalism of the gaps, an unfalsifiable entity proposed specifically to escape an inference the evidence keeps pushing toward. Consider what this strategy actually involves. When the cosmological argument is dismissed as God of the gaps, invoking an unseen explanatory entity to fill scientific ignorance, the standard response is to demand evidence rather than invoke the entity. Yet, when fine-tuning forces the same kind of inference, the response is to invoke an infinite multitude of unseen universes. The accusation against the theist is that one God is too speculative without direct observation. The naturalistic alternative is infinite universes, also without direct observation. The asymmetry is not subtle. What does it mean when the demand for evidence is applied rigorously to one position and abandoned for another? It means the dispute is no longer about evidence. It is about which conclusion the reasoner is willing to accept. CCC is not the multiverse, but it shares one feature. CCC adds structure to avoid the inference. It expands the cosmic picture from one aeon to many, hoping that the expansion explains away the specialness of any single aeon. It does not. The specialness is in the framework itself, the conformal structure, the reciprocal hypothesis, the lawful crossover. None of these are dissolved by extending the timeline. They are, on the contrary, magnified. An infinite chain of eons is an infinite chain of specialness. The aggregate is not less special than the part, it is more. Consider the logic at full extension. Suppose CCC is correct, and the universe consists of an infinite chain of eons, each smoothly tied to the next by the reciprocal hypothesis and the Weyl Curvature Hypothesis. The question that follows is where this lawful chain came from. Three answers are conceivable. First, the chain has always existed, without further explanation, a brute eternal fact. Second, the chain produced itself, somehow, from no prior conditions. Third, the chain was instituted by a cause prior to the chain. Examine each. The first answer abandons explanation. To say it has always existed and that is the end of the matter is not an answer to the question, why does it exist with this structure rather than another? The cosmologist who accepts an eternal lawful chain has accepted an eternal something, and is then no longer in a position to object that an eternal intelligent cause is one entity too many. The structure is already there. The question is its nature. The second answer, that the chain produced itself from no prior conditions, is logically incoherent. A thing cannot precede itself. To produce something is to act, and to act requires existing. The chain producing itself would have to exist before it existed. This is not difficult physics. This is impossible language. The third answer, that the chain was instituted by a cause prior to the chain, is the only one that does not collapse into either abandonment of explanation or logical contradiction. And that cause, by every standard of classical reasoning, must be itself uncaused, eternal, independent of the chain it produced, and possessed of the power and intelligence required to enact a lawful, mathematical, intelligible framework. Even Richard Dawkins, in interviews, has admitted that the origin of life on Earth has the appearance of design, though his proposed alternative is an extraterrestrial source rather than a terrestrial one. Whatever one thinks of his alternative, the admission itself is striking. The naturalist who looks at biological complexity and concludes, "This looks designed, but it cannot be designed by what we would normally infer," has not refuted the design inference, he has redirected it. The same pattern repeats in cosmology. The fine-tuning looks designed. The CCC framework, even if true, has the marks of design throughout. The redirection toward eternal physical chains, toward multiverses, toward unobserved auxiliary structures, does not eliminate the inference. It defers it. What does it mean when honest naturalists concede the appearance of design, but insist the appearance must be wrong? It means they are not following the evidence. They are filtering it through a prior commitment. The prior commitment is itself worth examining, but it should not be confused with the evidence. There is one further line of critique to add. Some defenders of CCC argue that even if the theory is currently incomplete, science will eventually fill in the gaps. The conformal factor problem will be solved. The mass fade-out will be explained. The empirical signatures will be detected with better instruments. This is, by any honest accounting, a kind of faith. It is faith in future discoveries that may never come. It is, structurally, identical to the response theists have sometimes been accused of giving, invoking unseen explanatory entities to rescue a position. The difference is that the theistic argument from fine-tuning, design, and the contingency of lawful structure has its evidence in hand right now. The scientific gaps in CCC are not currently closed. They are open, and there is no guarantee they will close. What does it mean that the strongest scientific critique of theistic arguments, the so-called God of the Gaps charge, applies in equal force to naturalism of the gaps? It means honest reasoning cannot accept the one criticism while ignoring the other. Either gaps are evidence against a position, or they are not. Consistency demands the same standard. Let us return to the original puzzle with fresh eyes. The early universe was non-generic. Why? The mainstream answer, inflation, relocates the puzzle. The CCC answer, inheritance from a previous aeon, multiplies the puzzle. Neither, by the admission of their proponents, has solved it. The non-genericity remains. When all proposed natural explanations for the universe's specialness either relocate the problem or multiply it, what remains? The evidence, examined honestly, points in a direction many modern cosmologists are reluctant to acknowledge but cannot consistently deny. The intelligibility of the cosmos, the lawful structure of every aeon, the precise calibration of constants, the suppressed Weyl curvature at every beginning, the conformal architecture that knits aeon to aeon, none of these are self-explanatory. They are not what unconscious matter produces. They are exactly what one would expect from an intelligent cause. Power sufficient to enact such a framework, knowledge sufficient to design it, and will sufficient to bring it forth. This is the part I return to often. Not because it is comfortable, because it is what the evidence supports. The natural explanations for cosmic origins, examined carefully, all reduce to the same residual mystery. The intelligible, lawful, precisely structured cosmos, whether single or cyclic, whether one aeon or infinite eons, does not explain itself. The persistent, honest response is to recognize that something intelligent stands behind it. What does it mean that the most audacious naturalistic proposal of the last 50 years, articulated by one of the greatest mathematical physicists of his generation, examined with full empirical rigor, still leaves the deeper question untouched? It means the deeper question is not, in fact, a scientific question. It is a metaphysical question. And metaphysical questions have metaphysical answers. Take a moment before we close this exploration. Think about what you have heard. The early universe was extraordinary. The proposed natural explanations for its specialness, inflation and conformal cyclic cosmology, either relocate or multiply the specialness. The empirical evidence for CCC is, after 15 years, weak. The theoretical structure is, by sympathetic admission, incomplete. And yet, the underlying lawful intelligibility of the cosmos remains, in every account, a fact awaiting explanation. What would you conclude from this evidence if you followed it honestly? Let me bring this exploration to a close. We began with a puzzle. The early universe, visible to us in the cosmic microwave background, mapped by Kobe in 1989, by WMAP starting in 2001, by Planck starting in 2009, was thermodynamically extraordinary. Its low gravitational entropy is acknowledged across the cosmology literature, even by those who do not draw theistic conclusions from it. Sean Carroll calls it an important puzzle. Roger Penrose calls it the central question of cosmic origins. We followed Penrose's proposal, Conformal Cyclic Cosmology, through its mathematical foundation, its observational claims, its missions, its critics, and its admissions. We saw the geometry of conformal rescaling, the reciprocal hypothesis tying one aeon to the next, the Weyl Curvature Hypothesis, the bold suggestion that the Big Bang was a boundary rather than a beginning. We saw Penrose, Vahe Gurzadyan, Christoph Meissner, Pavel Nurovsky, Daniel Ann, and Paul Todd develop and interpret the framework. We saw COBE, WMAP, and Planck deliver the data on which every empirical claim was tested. We also saw the critiques. Adam Moss, Douglas Scott, James Zebin, Ingun Vehus, Hans Christian Eriksson, Amir Hajian, Lopez and collaborators, Bodnia and collaborators, independent teams, independent methods, consistent conclusions. The CCC observational program has not produced signatures that survive proper analysis. Oliver Markwell and Chris Stevens write openly that the conformal factor problem remains a major open problem. Paul Todd writes that the QFT content of CCC remains all questions and no answers. The theory is, by the assessment of its own sympathetic interpreters, incomplete. And we saw the deeper failure. Even if conformal cyclic cosmology were complete, even if its empirical signatures were confirmed, It would not eliminate the need for an explanation of cosmic origins. It would push the boundary back. It would extend the chain. But the lawful, mathematical, precisely structured framework within which any aeon or infinite sequence of eons operates would still demand an explanation. Fine-tuning is not erased by multiplication. Specialness is not dissolved by extension. The evidence, examined honestly, points in one direction: the intelligibility of the cosmos, the precise calibration of constants, the suppressed Weyl curvature at every beginning, the conformal architecture, if it exists, that joins eon to eon. The very fact that the universe is mathematically describable at all. None of this is the product of unconscious matter. None of this is what randomness produces. All of it bears the hallmark of an intelligent cause. Power sufficient to enact the framework, knowledge sufficient to design it, will sufficient to bring it forth. This is the rational conclusion. Not because the science forced it, because the science, when followed to its limits, kept pointing toward it. The mainstream account has its own admission. The most ambitious alternative has its own admissions. Both, examined together, leave the same residue: a cosmos that cannot account for itself. If you found value in this exploration, in walking carefully through one of the most ambitious cosmological proposals of our generation, and seeing where its claims hold and where they break, consider subscribing to the channel. It helps these deep dives reach more curious minds. Now consider the last thought before we part. Roger Penrose may be right that the Big Bang was a boundary rather than a beginning. The mathematics, despite its open problems, is genuinely beautiful. Conformal cyclic cosmology may yet survive into the next generation of cosmology, reformulated, refined, perhaps even partially confirmed. Or it may not. The science will sort itself out, as science does, on timescales we cannot rush. But whether CCC is confirmed or refuted, whether the universe is one eon or infinite eons, whether the cosmos cycles or unfolds only once, the deeper question remains: why is there anything? Why is what exists intelligible? Why does the cosmos bear the marks of design, of calibration, of structured precision rather than chaos? The microwave background ripples through the sky at 2.725 Kelvin, carrying its faint patterns of 1 part in 100,000. It tells us about the universe at 375,000 years old. It does not tell us why the universe began with such precision. It does not tell us why anything is here to begin with. It does not, in the end, answer the question Penrose first raised. Why was the early universe so non-generic? It only deepens it. Not tragic, not triumphant, just unresolved. Good night.